In this activity, we're going to continue looking at the same transfer function that we were working with before, this aircraft model, and we'd like to do just a few more things with it to demonstrate a few other capabilities both within MATLAB and then also integrating some of the other things that we've learned in the course. So we're going to keep our existing time domain specifications in terms of our rise time and our overshoot. But now what we're also going to do is add in a constraint on our desire to have zero steady state error. And not only that, we're going to be interested in applying that constraint or that desire in terms of a disturbance step input. So everything that we've talked about here, this is with regard to a step in the reference. So what we're adding is a requirement to say that we want zero steady state error, but now with respect to a step in the disturbance. So broken this down into 3 steps. So the first one is simply looking at the plot that you stopped with at the end of the last activity and go ahead and evaluate the steady state tracking error. So this is again looking at the response due to a step in the reference. Then what we're going to do is we're going to take a look at the response in part B here. We're going to take a look at the response due to a step in the disturbance. And so in MATLAB, there's a nice way of doing this, and this includes adding an extra plot to your root locus. And so there's an option to go up to your toolbar and select Add Plot, and then it'll pop up essentially a generic feedback diagram, and you're going to select their term there it's called DU, essentially that represents a disturbance to the input U. So we're going to select that as our new plot. And so what I would recommend doing is go ahead and starting with this activity, do part A, muck around a little bit to see if you can get part B, but don't spend too much time, and then go ahead and advance the video and I'll show you how to pull up that plot, and then pause and try to figure out the rest of that by essentially figuring out this steady state error due to that step in the disturbance once you have that disturbance plot up there. And then after we quantify that, you're going to see that there's actually a pretty significant steady state error in the disturbance, which is a bad thing. And so what we're going to do is we're trying to fix that by adding a PI controller to what we're doing. And so since we started with a lead controller, keep in mind that, remember, when we talked about a PI controller, that had a KP term, which was multiplied by the error. So our input would be KP, our proportional gain, multiplied by the error, plus, and then it would be a KI multiplied by the integral of the error over time. And so these were essentially summed together, the proportional piece and the integral piece. And if you had the derivative piece, you could also have that in there. So now that we have this lead controller already in place, what we'll do is when we want to add in this integral term, what we'll do is we'll essentially make it additive. So what that means is we'll put this 1 in front to say that we'll keep this existing controller, and then we'll add another piece that includes this integral part. The consequence of doing that leads to having an extra factor of s, that integrator term, in the denominator, and then an extra 0 located at the ki, value of ki. So that's another 0 that gets added. We'll go through this step by step, so we'll add this first, and then we'll add this, and you'll see that if we only added this, the root locus looks definitely not what we want. So adding this extra 0 also helps to reshape that root locus. So go ahead and get started, do part A, and then if part B doesn't come very quickly, then just go ahead and watch the next steps of the video, and then pause again to finish off part B, and then try your hand at adding these 2 new terms into the root locus, and then tune that in order to achieve both our new disturbance criteria while still keeping these 2 criteria satisfied. So this is where we left off in the past activity. And so we had already achieved our overshoot criteria and surpassed our rise time criteria. And so what we're going to do now is take a look at the steady state error. So that's our first step. So that's pretty easy. We just add a new criteria, one of our new characteristics. So we select steady state. And then that gives us this blue bullet to highlight. And so it gives us a final value of 0.982. And so that's pretty good. So it's not 0, but that's pretty close. And so we're not going to see too much of a significant performance degradation because of that. So now what we'd like to do is go ahead and look at the disturbance step. And so that's what I've already got pulled up here, but let's do that again. So I'm going to go over to Control System, and there's a new plot option. So that new plot, I'm going to click that down, and so we're going to keep exploring all the different capabilities MATLAB has here. But the one that we're interested in right now is a new step input, and so that pops up a dialog box that looks something like this. And so you see this generic feedback diagram, and so these are the different signals that you can pull up. And so again, you'd select those selecting this way. So we already have the reference to the output. So that's what we already have been plotting. So what we're going to do now is this disturbance du. So that's this disturbance happening here to y. So you notice that if you wanted, for example, to have a disturbance that happened after the plant, you could choose this dy. So it depends on how that works. But in general, our disturbance happens here. And so we'll go ahead and click plot. And that pulls up a new disturbance plot that looks something like this. And so if we were to go ahead and right click and get our steady state tracking, we notice that we get a final value of 2.1. And so this final value is pretty large. And so our tracking error is quite large. It's essentially 1.1 over what we wanted it to be. And so that could be bad. And so what we'd like to do is add in a PI controller now in order to compensate for that. So we're going to pull up our compensator window. And so we are going to add two terms. One is we're going to add an integrator. So that's the 1 over s factor that goes in there. And so what happens is, if I pull this away just for a second, you'll notice that we get some pretty bizarre behavior. So you see the root loci now going out and into the right half plane, which means that this is becoming unstable. These poles now, where all these purple dots are, or pink dots are, this is indicating that we're very close to the imaginary axis, which is also why, for example, our damping ratio is very low, and that's leading to some pretty significant transient behavior. So if we go back to the reference to the output step function, now we've got an overshoot of about almost 60%. And so that's way beyond our specification at this point. So both just because it's the way in which our controller is formed, but also in order to solve this problem, we're going to add that real 0 that corresponds to the integral gain. So right now that real 0 is located at -1. And so what we get now is we get an overshoot of 8.8, which is a little bit bigger than what we wanted. The rise time is still fine, and now we get a final value that is 1. So now we're achieving even better tracking error when we look at the reference. When we go to the disturbance, now our final value is essentially times 10 to the -17, which is effectively 0. So that means that we've squashed that steady state error. We do have a little bit of transience, so that's a little bit undesirable. But right now, our design specification doesn't say anything about the transience in the disturbance, so we don't really have to pay attention to that. But it is something worth noting because that's a pretty large, almost 40% overshoot essentially on the disturbance. So let's focus now on the location of this 0 value. We added an integrator, which is always located at the origin, and we added some one extra 0, and so that's located at the point -1 right now. So I'm going to go ahead and zoom in a little bit. I'm going to click first on the root locus, and so that gives me the root locus editor button up here. It gives me this zoom button, and so I'm going to go ahead and try to zoom in a little bit closer. I'm actually going to leave out some of the stuff just so I can see what's going on here. So what we're seeing is these poles are really going to be the thing that's driving our overshoot that we don't want here. So so if I come back to the root locus editor and I no longer decide to zoom in, so I've got my tool back again, I can play around a little bit with this location. So we could see if I move this over here, then I get rid of those, I kind of reduce the size of this circle here. So that's still giving me some pretty large overshoot. So let's see if I can, so now I'm moving these dots. I think it's a little bit tricky. So if I move that a little closer, that might give us better behavior. So you'll see that when we're here, we're still getting pretty large overshoot because I've got these poles that are real close to the origin, these complex pair that are going to lead to the largest or the smallest damping ratio, which contributes to the largest overshoot. So they pull these down at some point. There we go. Now I'm getting something that is a lot better in terms of overshoot. So it gives me about 9.7 on overshoot. I still have this 0 here, and that's leading to a rise time that is much larger than what we had before. So that's 0.7 now. Whereas before we were having a much smaller rise time. However, this is now achieving our specification though. So even though we were doing a lot better on rise time before, this is still satisfying that 1 second rise time that we had in our design spec. And so something like this controller design would work. We now have less than 10% overshoot. Oh, actually, I just remembered. We want a little bit less overshoot than that. So what we're going to do is grab these poles and try to pull them down just that little bit further. See if we can get that to 5. And so now we're going to pull that down. There we go. We're right there at 5 now. And okay, so that even looks even better. So now we've reduced that rise time even again. But even if you were to look at 1 second, you've already gotten all the way up to 1 at that point in time. So even if you wanted to avoid this immediate peak and you wanted to evaluate rise time based on the time when it really is getting there and never dipping back below, then that would still be within our time domain spec. And then now we're hitting that 5%. So I forgot that it was 5 instead of 10. And if we, again, now that we've added that integral term, this disturbance steady state error is now at 0. So something like this controller design would work. And so then I'll just summarize a little bit and provide some other values that I think if I spend a little bit more time filling with this, we could get a slightly more refined controller design. But this achieves all of our time domain specs. And so for this particular example, I've moved the location of that integral gain to about 0.2, and my gain value is right here. And I haven't moved my lead compensator polar 0 there. Just to summarize what we've seen in this activity, we took a look at the steady state tracking error and we saw that it was actually pretty good. So we achieve a value that's very close to 1 here. So just a pretty small steady state error using that lead compensator. When we took a look though at a step in the disturbance, we saw a pretty significant steady state tracking error. So the output became 2.1. I think in the previous section of the video when I was dealing with the MATLAB, I kind of misspoke and called it 1.1 error, but it's actually 2.1 error because remember what we want from the error, we want it to be 0. When we look at the reference for the a step in the reference, we want to jump up to where the reference goes. So if the reference steps from 0 to 1, then we want the output y to jump from 0 to 1. But if we have the error do a step from 0 to 1, we don't want the output to go from 0 to 1. We want it to stay at 0. And so what we observed is that there was an error that essentially got us to about 2.1. So that means that y got up to about 2.1, and so then that error is the whole thing. So that's pretty big and something we'd like to compensate for, and so that's why we introduced this PI control. So that included a pole at the origin and also a 0 located at minus ki. And so we observed, you could have played with it a little bit more than I did moving that around, but when you place that 0 pretty close to the origin, such as like this, then that didn't end up affecting the complex poles, the other two sets of complex poles, and so that's an advantage. But it did redirect the branches back into the left half plane. So I showed you a solution that I got before. This is another solution. Just like before, there are many different controller designs that that you could use, and oftentimes that there are not only just time domain specifications, but then there's also what we might call comfort constraints or comfort design choices. And so that would include things like smaller gain values, something else that might affect how a system necessarily was not safe or unsafe, or achieved our goals or not achieved our goals, but made for example, a more enjoyable or more desirable ride, or just kind of other characteristics about the system evolution. So anyway, that's how we might include other constraints that we had already seen throughout the course, and also include other different controllers in conjunction with some of our newer controllers.